we saw that the X-ray tube produced, and we looked at different components in there and their functions. But for those components to work, there must be an X-ray generator. The X-ray generator works as the power supply for the X-ray tube. The electricity does not come from the source and go straight to the X-ray tube. Electricity must go through the X-ray generator such that that electricity is modified a bit for efficient production of X-rays in the X-ray tube. And we have different types of X-ray generators, as we are going to see. But we have one which is used more in the modern machines. Including the kV and MA, you are actually commanding the X-ray generator to modify the electricity such that the X-ray tube can produce X-rays according to the factors that you have fed into the machine. The generator used in the X-ray machine is called a high voltage generator. It's called a high voltage generator. And the reason why it's called a high voltage is because it has a transformer in there that steps up the voltage from volts to kilovolts. You know that the volts we receive from the mains are about 220 volts, but those ones are not high enough. The amplitude is not high enough, or the voltage is not energetic enough for efficient production of X-rays. So that voltage must be stepped up from volts to kilovolts, and those are the kilovolts you feed into the machine. If it is, for example, 80 kV that you have fed into the machine, then this generator in the high voltage generator, this transformer in the high voltage generator has to step up the volts from 220 to 80 kV. And then this voltage goes into the X-ray tube. This generator has 3 parts. It has the high voltage transformer, which is the step-up transformer to step up the volts to kilovolts. And also it has a filament transformer. This one steps down the voltage which goes to the filament. A filament has a separate circuit from that of the entire X-ray tube. The circuit for the filament is there to feed the filament a voltage and a current to heat it up for electron production. Then the X-ray tube as a whole has its own circuit also. That circuit has a high voltage transformer that step up the voltage to kilovolts. And also the MA that you feed into the machine is also done by that circuit for the X-ray tube. Is also fed into the machine by that circuit of the X-ray tube. So I've said that within the X-ray generator, we have the high voltage transformer. Its main purpose is to step up the voltage. It is connected to the major and the minor KVP selector. That is for selecting lower kVs and also selecting really high kVs. It increases the volts. It increases the volts from the auto transformer to kilovolts. That is, the secondary voltage is greater than the primary voltage because the secondary windings are greater than the primary windings. If you remember your physics, A-level physics, we looked at transformers and windings. The primary, in the transformer, we have a primary side and a secondary side. There are windings on the primary side and also there are windings of wires on the secondary side. If the windings of wire are few in the primary and many in the secondary, then that transformer is a step-up transformer. But if in the primary we have more windings than in the secondary, that transformer is a step-down transformer. It steps down the voltage. Those that don't remember, this is what I'm trying to say. We used to draw our transformers like this. And then we have the primary where we have these windings of wires. And this is the secondary and the primary. If you have few windings in the primary and many windings in the secondary, so if you look at it well, you realize that we have few in the primary and the many windings in the secondary. So this is a step-up transformer. This it steps in. Since transformers operate only on AC, I mean current, the waveform on both of us is sinusoidal. So what I mean is the voltage the primary side is sinusoidal. Also the voltage secondary side will be sinusoidal, though its amplitude is a little bit higher than that of the primary. So I was saying that the transformer works on only AC voltage, that is alternating current. So for example, if this is the primary side, this is the secondary side, the voltage in the primary is sinusoidal, though with a lower amplitude, and the voltage in the secondary is sinusoidal, though with a higher amplitude, if it is a step-up transformer. So the primary voltage is measured in volts. This one is measured in volts. Normally, it's about 220 volts, whereas the secondary is measured in kilovolts. Example can be like around 70, can be like around 70 kV. And also the primary current is measured in amperes, while the secondary current is measured in milliamperes. So this is what I've been talking about. This is our transformer in the high voltage generator. You see the windings in the primary are fewer than the windings in the secondary. And that's why you see the amplitude of the voltage in the primary is lower and the amplitude of the voltage in the secondary is higher. And both volts are sinusoidal. They are still alternating current. Now, within the same generator, we have what we call rectifiers. Within the same generator, we have what we call rectifiers. We have seen that we have a step-up transformer in that generator. Now we have rectifiers. The rectifiers, if you remember your electricity in physics, maybe in the high school, rectifiers, they are there to convert the alternating voltage to direct voltage or alternating current to direct current. Alternating current, that is the current which changes direction, or that is the voltage which changes direction, the sinusoidal voltage. The DC, that is the current that flows in only one direction. The X-ray tube that we use needs DC for production of X-rays. It doesn't need alternating current. This is because the X-ray tube has a cathode and an anode. The cathode should always be negative and the anode should always be positive. For this to be maintained, the X-ray tube must be supplied with a DC, always to make the cathode negative, the anode positive. If it is supplied with alternating current or alternating voltage, that means at one moment, the cathode is negative, the anode is positive, and another moment, the cathode is positive, the anode is negative. We don't want that change of polarity to occur. The change of polarity destroys the X-ray tube. So that's why the X-ray tube does not work on alternating current. It must only work on the direct current. So within the high voltage generator, we have these rectifiers that convert the alternating current to direct current and then goes into the X-ray tube. Rectifiers are diodes. A diode is a rectifier. If you remember your A-level physics, diodes rectify voltage. Current from the main supply of power from the sockets has a frequency of about 60 Hz. That means it changes direction 120 times in a second. If such a current is fed into the X-ray tube, the polarity of the cathode and the anode is going to change 120 times in a second. We don't want that. So when this voltage goes through rectifiers first, these rectifiers only allow electrons to flow in one direction. So although generators can work on AC, X-ray tube requires DC for electron flow in one direction. We want electrons to only flow from the cathode to the anode. We don't want a reverse flow. And that reverse flow can't happen because the anode does not produce electrons. Electrons are only produced at the cathode by the filament. So we want electrons to only flow in one direction from the cathode to the anode. So we need the DC in the X-ray tube. X-rays cannot be produced by reverse flowing in the reverse direction. So reverse direction is disastrous because cathode cannot withstand tremendous heat generated during production of X-rays. That is if the anode design can produce electrons. But of course, the anode does not produce electrons. So rectification is accomplished with diodes. And diodes can either be vacuum tube or solid state rectifiers or solid state diodes. Transformer, which steps up this voltage, like that, steps up the voltage. But then after, this voltage goes through these rectifiers. You see, these are rectifiers. These are diodes. If you remember the diode symbols, the voltage goes through the diodes and then it is rectified. You realize that the negative part of the voltage has been removed. The negative part of the voltage has been removed, and that means rectification. So we are only left with voltages in the positive, which are only in one direction. Then, within the same generator, I told you that we have a separate circuit for the filament. In the filament, this separate circuit of the filament has a step-down transformer, which steps the voltage down on the filament. So it reduces the current to the filament. And its main purpose is to heat the filament such that it produces X-rays. It produces electrons. So you realize that the transformer for the filament is a step down. We have many windings in the primary and a few windings in the secondary. So we have a lower voltage that goes into the filament to just heat it up and produces electrons. So the high voltage generation converts 220 volts of AC to kilovolts of DC. The voltage that we receive from the main is about 220 volts. So this generator converts 220 volts of AC to kilovolts of DC, and then goes into the X-ray tube. So the generator is a fixed component of the X-ray imaging system. Most of the things that it does are not under your control. It's only the kV and MA that is under your control. When you feed the kV and MA, of course, you're controlling this generator. But most of the things that it does are not under your control. For example, rectification of the voltage or conversion of the voltage from AC to DC is not under your control. Now, we have three types of generators. We have a single phase, we have three phase, and we have high frequency generator. So, the generator affects the quality and the quantity of the photons produced. The generator affects the quality and the quantity of the X-ray photons produced. The quality, I mean the energy, number of photons in the beam. Looks like my network is getting poor. Am I breaking?
You are clear, sir.
Okay, I was saying that quality, when you talk about quality, we mean energy of the beam. Quantity means number of X-ray photons in the beam. Now, the kV you feed into the machine affects the energy of the X-ray photons produced. If you use 100 kV and another person uses 80 kV, 100 kV, the X-ray photons will have a lot of energy than the ones produced at 80 kV. So kV affects quality of the beam. And also, to certain extent, affects the quantity of X-ray photons produced. This one will be expounded on more in the subsequent lectures. But right now, know that whenever these factors you feed into the machine, they have effects on the X-ray being produced. The kV has the kV determines the energy of the X-ray photons, and also to a certain extent the amount of photons in the X-ray beam. The MA, for it, only affects the number of photons in the X-ray beam. The higher the MA, the higher the number of X-ray photons in the beam. So, the unrectified voltage, if the voltage is not rectified, like it means AC voltage, this voltage waveform appears as the voltage waveform supplied to the primary side of the high voltage transformer, except its amplitude is much greater. When the voltage is stepped up, the output voltage in the secondary is of a higher amplitude than the input voltage in the primary. So if this voltage goes to the X-ray tube, the current passing through the X-ray tube exists during the positive half cycle. That is when the anode is positive and the cathode is negative. During the negative half cycle, current can only flow from the anode to the cathode, and we don't want that to happen. This does not occur because the anode is not constructed to emit electrons. So this voltage has to be rectified before it goes into the X-ray tube. And rectification also has types. We have the half-wave rectification and the full-wave rectification. That's what we are going to see. Half-wave rectification, photons are produced and conducted only during the positive half cycle. So you see this illustration. The wave The red wave shows us the alternating voltage. Then this green wave shows us a voltage that has been half rectified. That is, the negative half cycles are removed from the equation, or they are removed from supply. You can see that very well. So only the positive half cycles are left in the supply. So you see, with this kind of rectification, the X-rays are produced in pulses because they are only produced when it is a supply. At this point, there is a supply, there is a supply here, there is a supply here. So you realize that X-rays are going to be produced in pulses. There are times when the voltage is zero. So here, these points here, we don't have any supply of voltage with the X-ray tube. So there is no X-ray production. At those points, there is no X-ray production. X-rays are only produced when the positive half cycle flows through the X-ray tube. So in this case, we have 100% voltage ripple. And what I mean by 100%, I mean that the voltage falls from the maximum to zero. We call that 100% voltage ripple. It falls from the maximum to zero. That means energetic X-rays are only produced when the voltage is at the maximum. When it is falling to zero, the system is only producing low energetic X-rays. High energetic X-rays are produced when the voltage is at the maximum. So this kind of generator is inefficient at X-ray production. It even makes exposures longer and also contributes so much to the patient's radiation dose because it produces a lot of X-rays that don't have enough energy to penetrate the patient. So they just become absorbed in the patient and increases the patient's radiation dose. So normally the half-wave rectification circuit is composed of only two rectifiers or two diodes. They are enough to do what we call half-wave rectification. When the voltage is going through one side, these diodes can allow it to flow, but as it changes direction, then that voltage is stopped, doesn't go through the X-ray tube. So in your free time, you can look at these illustrations and you get to understand what I mean. So in half-wave rectification circuit, resulting electric current is a series of positive pulses, as we have seen. The resulting electric current is a series of positive pulses separated by gaps when negative current is not conducted. It's a series of positive pulses. We have seen it. This is a pulse, this is a pulse, this is a pulse. These are separated by series of gaps when the negative voltage was removed from the system. So resulting electric current is a rectified current that causes electrons to only flow in one direction, and that is from the cathode side to the anode side. Only one half of the SC waveform appears in the output. That is, only the positive half cycles of the voltage appear in the output. So this one will produce about 60 X-ray pulses in a second. It will produce about 60 X-ray pulses in a second. One disadvantage of half-wave rectification is that it wastes half the supply of power. It wastes half the supply of power because the negative voltages have been removed. That power has been lost. It also requires twice the exposure time. The time of exposure is prolonged. If it was to be for 5 milliseconds, for example, if we are using a full wave rectification and exposure is 5 milliseconds, for half wave rectification, the exposure will be about 10 milliseconds. And these long exposures, they increase patient's radiation dose. So for the full wave rectification, the entire AC waveform is rectified. So you can see here, this is an AC voltage. This is AC. This is half wave rectification, and this is full wave rectification. You see, full wave, the negative cycles of the voltage were converted to positive. Instead of removing them from the system, they were actually converted to become positive. So here, we are not wasting power. We are utilizing both cycles. But again, this has one problem. It has 100% voltage ripple. The voltage falls from maximum to zero before it goes back to the maximum. Though we don't have gaps in this case. Here, the time of exposure is shortened than how it is in the half-wave rectification. Again, this system, much as the time of exposure is reduced, it is inefficient because of that 100% voltage ripple. Meaning, it is also producing low energetic X-ray photons. A high number of them, a bigger number of them is produced. Energetic X-rays are only produced when the voltage is at the maximum. So the negative half cycle is reversed so that the positive voltage is directed across the X-ray tube. So full wave rectification, you can use rectifiers 4 or more. Can be 4 in number or even more. You saw that for the half wave rectification, we only use 2 times. For the full, we can use 4 or even more to fully rectify the voltage. So current through the circuit is shown during both positive and the negative phases of the input waveform. Onyak James, are you asking anything? So in this case, there are no gaps in the output waveform. In both cases, the output voltage is positive. The main advantage is that the exposure time for any given technique is cut in half. The exposure time for any given technique is cut in half. But also it produces pulsed X-rays because you realize that the voltage falls from the maximum to zero back to the maximum. It is also producing pulsed X-rays. Though now it will produce 120 pulses in a second. For the half-wave rectification, it was producing 60 pulses. This one is producing 120 pulses in a second. So the previous types of wave rectifications are of a single phase power. Remember, I told you that we have three types of X-rays, of generators. The single phase, the three phase, and the high frequency. What we have looked at, the rectifications, we've been looking at only a single phase power supply. But these things can also happen in the three phase. A single phase, that is a generator that works on a single phase power supply. Single phase generator is a generator that works on a single phase power supply. Most of the power that we receive in our houses are single phase. Most of the power we receive in our houses at home is single phase. If you have ever come across these electric poles that carry more than 3 wires, for a good example is these metallic poles that we all know exports power to neighboring countries. They have more than 3 wires. Those ones carry three-phase power. They carry three-phase power. But the power which comes to our house is single phase. So there are some generators that work on single phase, other generators are working on three phase. X-rays produced when single phase voltage waveform has a value near zero. That is when the voltage is going back to zero. The X-rays produced at those moments when the voltage is falling to zero are of little diagnostic value because of their low energy, and therefore these X-rays have a low penetrability. When the voltage is falling to zero, at those points when it is falling to zero, the X-rays produced are of low energy. They have low penetrating power. They cannot penetrate through a patient. They will just become absorbed in the patient and increase the patient's radiation dose. It's only X-rays which are produced when the voltage is at the maximum that will have a high energy and will penetrate through a patient and will intercept the image receptor for image formation. So one method of overcoming this deficiency is to use some sophisticated electrical engineering principles to generate three simultaneous voltage waveforms that are out of phase or out of step with one another, which we call the three-phase electrical power. You know, single phase power carries only one voltage. Single phase power carries only one voltage. Three-phase power, they carry three voltages which are out of phase with each other. This is what I've been talking about. This kind of electric poles, they carry three-phase power system. So this thing is not clear here. But with this power, or work, James, mute your microphone if you can hear me. or work, James? Mute your microphone. Now, with this kind of power supply, for example, if this is the first voltage, this is the first voltage. The second voltage is out of step with the first one. Is out of step with the first one. What I mean is that they don't move together. And then the third voltage is also out of step with the first and the second. So when you look at them, they are actually 3 voltages. These are not rectified actually. Now, the good thing about this voltage is that when one voltage is falling, another one is coming up. When it is also falling, another one is coming up. It's like the voltage will never fall to 0. The voltage will never fall to 0. Now, if these voltages are fully rectified, whereby the negative half cycles are transformed to become positive half cycles, the voltage becomes fully, almost constant. Is that clear, members? Members, is that clear?
Yes, we are following you, sir. It's clear.
Yes, sir.
Okay. So that is what a three-phase is about. As one voltage is going down, another one is coming up. When it is also going down, another one is coming up. So the voltage will never fall to 0. And if they are fully rectified to remove the negative half cycles, the voltage becomes almost constant. So this one is very efficient at production of X-rays. But the bad thing it has, actually not the bad thing, I don't know, the disadvantage that this generator has is that bringing three-phase power supply to your facility is expensive. It is even more expensive than the cost of the machine you're bringing it for. If the X-ray machine, for example, is for 150 million Uganda shillings, and it has a three-phase power generator, it has a three-phase generator. That three-phase power supply, bringing it to your facility, it can double the cost of that machine. It can cost you about 300 million. So nowadays, it is very rare to find a three-phase X-ray machine, be it a CT, be it X-ray machine, because the cost of bringing a three-phase power is high. So the machines used nowadays, they are high frequency. They have high frequency generators, which can work on single phase power. Of course, high frequency generators can work on both. They can work on the single phase power, they can work on the three phase power. But since three phase power is costly to bring on site, we use single phase power supply and high frequency generators that can work on that single phase power supply. The high frequency generator can make the voltage to appear very, very constant than even three-phase power, than even three-phase generator. The voltage ripple in the three-phase generator ranges between 4 to about 16%. But for the high frequency generator, the voltage ripple can be about 1%, meaning that the voltage that we supply the X-ray tube is almost constant, is almost the same. So in three-phase power, here multiple voltages are superimposed on one another, resulting in a waveform that maintains a nearly constant voltage. The voltage impressed across the X-ray tube is nearly constant, never dropping to zero during exposure. It never drops to zero during exposure. So this is a single phase. This is the three phase. The voltage never drops to zero. This is the three phase that has been rectified. You see the voltage ripple. Okay, so today I'm going to stop here. There is an engagement which I'm going for. That's why I requested to meet you just for 1 hour. The next time we meet, we are going to continue with the high frequency generator before we move on to another topic. So on Wednesday, you will join again in the generators, and then we'll finish it, and then we'll move on to another topic. What is a ripple? I said a ripple means voltage drop. When the voltage is dropping from the maximum to zero, we say that is 100% voltage ripple. But here in the three phase, the voltage will never drop to zero. So that's why we don't have 100% voltage ripple. The ripple ranges between 4 to about 16%. Understood? Ongole Cole? Your name is difficult to pronounce. Is it clear to you, the person who asked? Okay, let me answer a few questions if you have any, and then we close. Are there questions?